Alright, so in this video, I'm going to be going through this worksheet a bit. I'm actually going to start with number 2 because it's easier. So, drop a stairwell off the balcony and record the time it takes for the ball to hit the ground. I don't know how long that took, but I'll just give an example. Let me think. I'm going to say it's going to take about, it takes 2 seconds. I don't know if that's reasonable or not. We'll see. We'll see. We'll be able to tell when we get the height, because if we're getting a height of like thousands of feet, then we're probably not right. Okay, solve the position equation for initial position in terms of t. Hint, what is the initial velocity and what is the position of the ball when it hits the ground? Alright, so this is what I was talking about earlier about needing to orient yourself correctly. If this is the balcony, like this, I know it's a stair thing, but just pretend you're standing up here. And then you throw this, no, you don't throw it, you drop it. You drop this ball until it hits the ground right there. Okay, this balcony has some height h. You're dropping the ball. So what is the initial velocity? It's 0. Oh, now he wants you to do all this in feet per second, huh? Grr. I don't like English system. Okay, 0 feet per second. That's the initial velocity, because you're dropping it. It hasn't had any time to be accelerated. So then, position equation is y of t. I'm calling this the y axis here. That's a negative y. Equals 1/2 at squared plus v naught t plus y initial. Well, y initial, see, again, it depends on how we orient ourselves. Let's see here, y initial. You could call this the 0, or you could call this the 0. I'll actually show you that you can do it validly both ways. So first we're going to call this one the 0. So this is 0, 0. That means that the initial position of this thing is 0, right? That makes sense, because you know you're starting at 0, 0 and you have 0 velocity, so you're just dropping it. So we don't need those two terms anymore. So then we know that y of t equals 1/2 at squared. The acceleration of the Earth is negative 32 feet per second squared, approximately. And so you can also say that's negative 16 t squared, just taking that half into account. All right, so do not plug in time yet. Okay, and that's for the y of t. So this one just asks you for this one. Negative 16 t squared equals y of t. Plug the time into your new equation and find the height of the balcony. Well, then wouldn't it? All right, so y of t, what is, let's see here. Okay, so we need to find the time it takes to hit the ground. And however long, and this y of t, that's a distance value. This is basically, this bit is telling you, under the Earth's acceleration, how far will this thing go in a given time? So if you just drop it, how far is it going to go after t seconds? Well, y of t, that's just our h. And so this is what we're trying to find. So our height equals negative 16 t squared. That's what we're trying to find. T is 2 seconds. And then you get 4. 16 times 4 is 64. And your height is 64 feet, which is probably a little high. So this might be more like 1.5, 1.6 seconds. But I think you get the principle, and I hope you can, I hope it's fairly straightforward why you don't need those terms anymore, because you're dropping it, which means you have an initial velocity, and we're calling this the origin. Equally valid, you can say, this is my 0. Oh, sorry, that was, okay. So, if you plug in your thing, you're going to end up getting a negative distance. You would actually get h equals negative 64 feet. And it seems like you did something wrong at first, but after closer inspection, it makes sense, because you're starting here and you're going down 64 feet. And so that's why there's a negative sign attached to it, because it's a directional quantity. You're going down 64 feet from the origin, which makes sense because you're dropping it. Okay, so now I'm going to say, what if this is my origin? Well, okay, so our initial velocity is still 0 because we're still dropping it from above. But our initial position is going to be the height, right? Because if we're starting here, down here, however high we started up is just however high this balcony is. So then I'm going to get y of t equals 1/2 at squared plus h. And then if you plug in the acceleration, you get y equals negative 16 t squared plus h. Now, this right here is going to give you the height, the distance from the ground at this point, at that point in time. Well, you're on the ground. It's 0. So hopefully that makes sense. At some time given by t, this thing is 0 feet off the ground. Subtract h over, and you get h equals 16t squared, and then h equals 64 once again. Now this time, instead of solving for, this, you're solving for the initial position, but it's essentially the same calculation. You're just orienting yourself in a slightly different way. And for this particular case, you're just saying, here's the ground. How high would I have had to start up to get there in that amount of time? Also given by, the same relationship. So you can see that, there's more than one way to, there's more than one way to go about doing something like this. And with this one, you do end up getting a positive answer, because this is the ground, and this is your height, and your height is a positive quantity because it's going up like this, where in the last case you were saying you start here and you're dropping it, and in that case, it looks like a negative quantity because it's going down from the initial position, and here it's going up from the initial position. But those two are the exact same thing. All right, let's look at this other problem. Sorry about this. Okay. So, measure the height of your arm when you throw the tennis ball. Okay, this is a little different than what we did last year. Measure the height of your arm when you throw the tennis ball. Oh, I got it. It's saying, like, you're standing like this. Measure that. Okay, so that's going to be your initial height. So, okay. Let's see what's reasonable for that. I don't know, height of arm in the air, let's say 6 feet. If you're on the shorter side. Record the amount of time that the ball was in the air. Say 5 seconds. Don't know if that's reasonable or not, but we'll find out. Okay, find the initial velocity of the ball using the position equation. Okay, so our position equation, y of t equals negative 16t squared plus v naught t plus the initial position. All right, well, our initial position is the height, because that's where we're starting. Y of t equals negative 16t squared plus v naught t plus 6. All right, so let's see here what we're looking at. So we're trying to find the height at which this thing is hitting the ground. So we're going to call the ground our 0 over time. And at time 0, we're at 6 feet. So we're like here. And so this graph is going to look something like this. All right. And then there's like a little invisible bit. So when you solve for your zeros, you'll also hit that one. But just disregard it because you're not going to have a negative time. So then this is our vertex. That's when it's at its maximum height, so that'll probably be useful to us later. Yeah, exact time when it reaches its maximum height. So max height, and that also occurs when the velocity is 0, because we have that horizontal tangent line. So find the initial velocity, and the initial velocity is this slope right here, because that's the velocity when you start off. Well, we need to find some sort of, we need to find when this time occurs. Well, this time that we're looking for, we know 5 seconds. Here we go. We know that at 5 seconds, y of t equals 0. So let's do that. 0 equals negative 16 5 squared plus v naught 5 plus 6. Okay. And then I'll use my calculator real quick. And you just need to solve for v naught. So v naught is going to be 16 times 5 squared minus 6 over 5. .8 wow, okay. 78.8 feet per second. That's really fast. Am I doing that right? Let's see, 16.5 minus 6. Looks good to me. That's the initial velocity, even though that's insane. Okay, find the velocity of the ball when it strikes the ground. Alright, so if you take the derivative of this equation here, you end up with v of t equals negative 32 t plus v initial. All right, well, we know our v initial, so it looks like we're off to a good start. And when it hits the ground, we're at time 5 seconds. So 5 seconds here, negative 32, just because I had the power rule when we get the initial actual Earth acceleration again. And then v of t is what we're trying to find. V of 5 is that. And so then we just plug it in. Negative 81.2. And you might say, well, why is this number negative? Well, it's because when we're going down here, our velocity is, sorry, I shouldn't put that earlier there too. Our velocity is negative because we're heading down towards the ground. I mean, it makes sense. We're coming back down towards the ground from up above. And so our direction is down, and that's in the negative direction. And also notice that because you threw it from up above, like if you had done to here, right here, that would have the exact same velocity because parabolas are symmetrical. But because of the height of your arm, it's being allowed to fall a little longer. And so that's why this number is a little bigger than that number. Find the exact time when the ball reaches its maximum height. Well, when it's at its maximum height, we determine v is 0. So we'll just set this equation to 0. 0 equals negative 32t plus 78.8. All right, we're just trying to find out when the velocity is 0. And so we don't know what the time is, but we know when v of t is 0, the v of t term is going to be 0, and we already know our initial velocity term. And then so t equals negative 78.8 over negative 32, and that's going to be 2.463 seconds. And that also matches up with our the intuition we've established, because it's going to take, this is if we were only going to here, if it had been thrown straight off the ground, that would be the halfway point. But since it has to fall a little longer to get back, to account for the height of your arm, this is going to be, half of 5 would be 2.5, but it's a little less than that. And so that answer definitely makes sense. And find the height of the ball at this time. Well, now we have our position equation, and we have a time that we're interested in. And so then we just say y of 2.463 is negative 16. I'll call that thing phi squared plus g naught 78.8 phi plus 6, and you get, hold on just a minute, $103.023 feet. And so that's how you go about doing a set like this. You're just looking for relationships. You have your 3 equations. You can just start with one of them and either take the derivative or integrate if you ever forget what you're doing. And if all else fails, you can just say A equals 32 feet per second squared. And if you know that A equals dv dt, then you can derive the entire set yourself. But it's probably just easier to remember them. So that's it. Having a ball in the air for 5 seconds is maybe a little bit ridiculous, but it's very interesting to see that all you need to know is how long a ball is in the air, and you can figure out all of these things, which really shows you that it all comes down to this acceleration, and there are only so many things that can happen within that acceleration. And so when you're integrating, you're building your constraints and saying, if it's in the air for this amount of time, if it starts at this velocity, those have to be related together that way in order to make sure that the ball is always accelerating that much, because that's what it's ultimately coming down to. That's the force that's taking an effect on this ball, gravity.